Hi everyone, welcome back to Dragonfly Engineering. So this week we've got, unfortunately, a mold repair, an injection mold repair. And this is the mold. I've already fixed it, so this is like in the future. But two of these core pins basically bent in the process of molding. And it wound up with a defect in the part. And I can show you, probably overlay a picture right here of the defect. But you can see how these spindly 1/8 inch or 3.2 millimeter pins basically got pushed to the side of the mold cavity, and you see the shape of them in the part itself. Um, so a good part looks like this, and the reason why those long spindly pins are in there is for these holes on the ends of this part. And and basically these holes exist for sink control. Because in an injection molded part, if you have thick plastic, then the plastic, when it solidifies in a mold, will sink in and you get something called a sink mark, which is basically just a collapse of the plastic. So to prevent sink marks, you put core features or thin wall features in your plastic part. So whoever made this mold wound up putting these pin holes all the way through the part, which are kind of a hassle because it results in very fragile, spindly parts of your mold that can wear out and then deform, and then you got to take the whole mold apart and fix it. This big hole on the end also had some damage, and I don't know if that long pin, which is actually on the B side of the mold on this side, was the cause or the victim of the other pins deforming. And basically, these pins have a pointed tip, and when the mold closes, the pin is seeking out a hole in the B side, and the tip of that pin goes into a retainment hole on the B side. So you get this pin of, or this cylinder of metal that is spanning the cavity of the mold that creates that hole there. But if the tip of that pin doesn't find its retention hole on the other side of the mold, then it'll hit the side and then just buckle. And something like that happened. It's also possible that the pin actually did get in the hole, but the side force of the plastic injecting into the mold itself has to go around that pin, and it could be that the friction and hydraulic resistance of the viscous plastic passing around that pin length caused it to pull out of its reference hole and then buckle against the side of the mold. We'll probably never really know, but I got new hardened shafts of, or basically core pins. And in this episode, I show how we basically cut the new pins and install them in the already broken down A side. I didn't record pulling the mold off or taking it apart, but I did record reassembling the mold. And you'll see some interesting things like some coolant features and how they get up into the core and back out. So, hope you enjoyed this episode, and thanks for watching Dragonfly Engineering. All right, so we're over on the workbench. I've already taken the mold core out, plus this inner core to the mold core, that oval shape there. And I've pulled the two bent pins out, and they actually broke as they were pulled out. And I effectively had to use like a hammer to reverse hammer them out, and you can see that ball peen hammer I used, and basically just slowly tap them out, except that they broke because they were so bent, because there's a precision hole that a straight pin was intended to go through, but a bent pin coming out had to get busted up a few places to get it. So I attempted to straighten one and realized that it couldn't be straightened because it's hardened steel. So I pulled out the sister pin on the other side and got dimensions, because it's difficult to measure accurately a pin that's all bent up. And then we just mark them and put that guy back in there to make sure that I keep the correct one in the right spot. And I'll even measure the other one to confirm. As it turns out, these pins didn't have to be super accurate because they just kind of fit into a hole, a reference hole. And then to cut these, I usually just, for this kind of repair work, hand work, I just use the die grinder with the composite carbide fiberglass blade. which is about 1.5 millimeters thick. It's really thin and nice to cut. And typically you just use the blade guard as a pin stop to cut these pins to length. It's pretty quick and easy, and makes a good cut. But then you got to clean up your cut, and I always cut these pins long so that I can grind them into the correct length. And for kind of hand repair work on molds like this, I typically keep it simple and quick. And I use the trusty Home Depot style disc grinder, and I don't really do a setup. I just kind of sneak up onto the final dimension. So it's faster just to slowly come up to your dimension than going through a whole mill setup or a surface grinder setup. I just take a few thousandths off at a time. And again, as it turns out, these pins don't need to be super accurate anyway, because they pierce through a reference hole. You do have to keep the tip cool. If you start to see discoloration in your steel, that means you've probably started to anneal the steel. So keeping it nice and cool with the water right next to you is pretty important. Here we're cutting in the D-shaped profile. For some reason, the mold maker wanted these pins to be clocked or oriented, so the D-shape was added to the bases. It's not really needed. So now we're over on the surface grinder, and we've got a spin fixture, which is that tool behind my hand there, and it receives a ER32 collet, which is what I got in my hand there. That's a spring collet with the spanner wrench nut on it, and you just stick your part through and string most of it back through the spin fixture. That fixture is actually hollow, so you can have like a really long rod go through it. You just can't see the back off camera. But there's just a handle, and you manually spin this thing while you're grinding your round object. So you don't really need a super fancy like lathe style grinding setup. You can just get one of these handheld or hand operated spinners, and as long as you keep it spinning while you're grinding, you get a pretty good cone shape or cylindrical profile. So now I'm just pulling, or I was drawing the blade down, or the grinding wheel down. The Z-axis is a knob up to the right. And this grinding wheel is actually a diamond wheel, so it's mostly an aluminum disc, precision turned, with a industrial diamond and nickel coating on the outer perimeter. There you can see how I'm dropping down the grinding wheel. You want to spin as you're approaching, and you also want your part to be on the outspin side of your grinding wheel, as you can see I've got there, so you don't jam up your part and crash everything. Yeah, and then you just advance while you're grinding and keep spinning, and you can cut pretty good shapes and round parts with a surface grinder. And this isn't a precision shape or anything. I just needed a good point on the end. That wasn't. It needed to be a little better than what the sander did in the previous the previous scene. And then you just use a spanner to release your spring collet nut and pull the part off. Got a little close in there. I had to bring the grinding wheel up. All of this is on a mag base or a mag chuck, and that way you can orient your angle of your tip. And then be sure to stick your nut back in, otherwise you'll lose it forever. There we go. All right, now we're deburring or polishing that tip, and this is a deburr wheel, which is basically high-density cloth with a whole lot of slurried, or not wet, but impregnated grit in it, and it's real good for just taking the edge off of metal parts or polishing up your parts as well. Okay, so we're back on the bench with our two new pins. And I'm just kind of cleaning out the coolant they're not through lines, but they're actually just dead-headed holes. And with the cell phone, you can see a little closer that basically there's just some some pockets there that cooling water shoots up into and then comes back out. And the mating surface of that actually has a baffle in it. So water comes in one side, and there's a sheet metal wall that bifurcates the mating port of this, and that allows water to shoot up one side of that hole and then change direction and come back out the bottom, because you do need to cool off these mold cores. I'll show you more of that when we go to the main mold next to the molding machine. So there we're putting our pins in with a little D-shaped profile, and those are flush fit, and then they're going to be retained with the back wall of the bottom pocket of the mold itself that is over by the molding machine. And this oval shape is surprisingly accurate. It looks kind of rough, like the receiving oval and the block in the background almost look like a bandsaw cut, but it actually is a very precise fit. So there's a slight angle in that oval shaped core, and a matching receiving angle on the wall, or a draft angle. And then when I put those in, it basically fits exactly right, so that the back edge or the back surface is flush with the back surface of that subcore. So here we put it in. You got to make sure there's no particulate or obstructions to prevent a perfect fit. So that's finger tight, but then if I just give it a little tap with a rubber mallet, and you hear when it seats, and now it's perfectly flush. So kudos to whoever originally made this mold. That was a really precise fit. Yeah, it was no flash or anything in the final part. So there's our new 2 pins that we added. Now these bronze parts in the foreground are called lifters, and those will lift up and move together to allow the plastic part to get past the little ledge that my thumb is on right now. Okay, we're over by the molding machine, and this is the A-side mold block, and this is the cavity where that insert is going to go back into. So whoever assembled this mold last used this silicone adhesive to, I guess, bolster the seal on these O-rings that I'm pulling out. And then you can see in those water ports that there's a sheet metal wall that bifurcates that port. So cooling water comes in from the top edge of this mold through like a drilled hole, and it hits that baffle and it redirects it up into the holes that we were looking at in that oval shaped core insert. And then basically that water redirects off the blind holes in the core, and then shoots down the other side of that baffle and out. So it's an interesting way to inject cooling water up into a dead-headed drilled hole, and then it will redirect out the other side. Here I'm using some white lithium grease to seal the O-rings instead of using that silicone red glue. And this lithium grease I also use to grease up the angled lead pin holes, which is at the top of this core or pocket, which also houses the die springs, which will push those bronze parts, those the lifters. That's what applies the force that they actuate when the mold opens and closes to create the undercut in the plastic part that's molded up there. And then I'm cleaning the mold core itself, or the subplate. You got to make sure everything's nice and clean as far as dust or chips or plastic particles or anything. You got to get all that out of there because it's surprisingly precise. For instance, this shows the proper fit of an insert into a mold, where you can't really just stick it in with your hand, but you got to get it perfectly aligned and then tap it in with like a rubber mallet. And it actually does have clearance, but it's only about 1/1000 or 25 microns per side, and this is how a mold insert should go in. You just can't push it in, otherwise it'll angle lock. But you get it nice and parallel, and about halfway in it's fully aligned, and it'll just slide in like an engine cylinder or something. All right, in the back of the mold, that is the nozzle sprue insert. So basically the hot plastic squirts into that hole there, and it's relayed to the front runner system of the mold itself. And then here's the bag of goodies. So you can see 2 greased up springs, and those are what pushes the lifters forward and back, those brass parts right there. And those are in an angled guide in this mold, which is also a complicated part or feature, which probably was cut with a wire EDM. And yeah, you got to clean everything. These are shoulder pins. Excuse me for getting the camera. And those shoulder pins go down the center of those springs. And I'm just testing the fit right now. Actually, the shoulder pins go through the back plate, which is actually on the floor, and it's my work surface right now. But I'm just making sure that they screw in and they're greased up and ready to go. But the outermost back plate of this mold half has a couple of angled divots that allow those springs to rest against and be pre-tensioned. And then those guide pins are just extra guide so that the springs don't like buckle over time. They just stay nice and linear in the direction of force. All right, and then I put the screws in that holds that mold insert in place, and I think I am looking for the ever missing correct hex key in my index, which I found here. And we will tighten down all of the, I think there was 6 screws that held that mold core in place. I'm not sure why there was 2 extra ones kind of not in the corners, but yeah, whoever did it must have had a good reason. You don't want to tighten these kind of like they are an engine head. You don't want to fully tighten one side, but you want to have equal, you want to kind of go around as you tighten. Here I'm just checking the action of those lifters. You can probably see the little undercut that gets out of the way when the molded part needs to eject off of there. There's also some decommissioned parts of the mold. You can probably see some cam pins and some heel blocks in the back there for a part that's no longer actually molded on this mold. Yeah, there you can see. But I'm mostly interested in those bronze lifters moving smoothly. All right, and then we will pull the mold off of the backer plate, which is an emergency work surface, because these parts are heavy, so they don't really just slide around on concrete so easily. And then, yeah, you got to check to make sure that everything is clean. And I oriented the mold so I could hook it and load it back onto the molding machine as well. And then, yeah, so we're going to wipe down these surfaces. Because if you pinch, like, any contamination, metal chips, plastic pellets, or just crap from the floor, then your mold is going to be out of square when you bolt these 2 plates together. And then that will mess up everything. It could actually cause problems for your molding machine if you don't have a parallel mold loaded in there. So I'm real careful to make sure that everything's clean. And then we bolt the backer plate back on. I need to get a torque wrench. Right now I think I just used a piece of electrical conduit to extend my hex key there. Of course I didn't have the right one. You do want these bolts to be pretty tight, and I don't have a spec for you, but you do want to do the extra tightening because these plates can loosen up over thousands of cycles of these molds. You know, because there's like 150 tons of force being applied and then released off that plate. So it can slowly loosen on you. And finally, we will put our shoulder pins back into the holes that guide those springs for the bronze lifters on the other side. And then with that, we will load our mold back into the molding machine after we tighten these up. Probably could have edited some of this out. I'll show you the whole process. Here we go. That is the A side reassembled with our new pins. Oh yeah, so there are quick release hose connections, and those are the water lines that go, 2 of those go to the interesting little baffles. And that was the bent part before. And now we are going to reload our mold. You can see on the back of that mold, that's where the ejector plate interfaces the molding machine. And there's 2 hex bolts there that interface with external push rods. So there's 3 connections. The inner hole has a threaded rod that pulls the ejector plate back, and the other 2 hex locations, left and right, are for push rods to push the ejector plate forward. And those push rods basically come out from the platen of the molding machine. We're on the other side now. All right, and that's it. All right, we are going to try out the new to me mold heating unit. So this thing basically it's got water in it, and there's a pump that takes in the return water from this manifold stack, and then it centrifugal pumps the water into this basically metal pipe that's full of water and a whole bunch of electrical, probably hot water heater elements that go the whole length of this metal column. And then the hot water comes out to this manifold and goes into our mold. So I've got temporary water lines that come into the mold, come across the jumper into this side to heat up our mold halves using the cooling lines, and then we go back to the return on this mold heater. So I did just top off the water inside of the unit with the with this bucket that's got some old emulsion coolant in it, and we gotta be sure to open the input and output. And I will close this enclosure. Safety first. And we've got the power. Okay, so we flip the power switch on. Our temperature controller is here. We're set to 200. It's a little wonky. Actually, we're set to 250 degrees Fahrenheit. So that's about 110 degrees C. And then we hit push start. and we are pumping water through our mold. Probably a good idea to look for leaks. I don't see any leaks. And I think it's important to feel that you're actually moving heat so that you don't wind up boiling off the heater inside of this unit. But you gotta wait a few, like maybe 1 minute, and then the relay will kick in. So there's a time delay, probably just to ensure that water is flowing. I don't know if there's like a immersion sensor that will turn off the heater if it senses that there's no water in there. Not sure. But I've used this mold heater already and it works. Let me get the rattle out of it. And once this output turns on, we will check that heat is going out and heat is coming back in. So I'll be back shortly. All right, we're back. So the heater's now running, pump is running. I did top off the water system with the coolant. That's it's pretty nasty, so I'm not going to show it to you. But there's a pump in here, and I topped off with this hose to make sure that this water circuit had water in it. And this is the return hose from the mold over there, and I can feel that it's hot. And this is the outgoing hose, and it's hotter. So we are dumping heat into the mold, and we are actually flowing liquid back. It's important to make sure that you're actually flowing liquid, so you need to feel both out and inlet hoses to the mold heater are hot. Otherwise, the actual chamber that heats the water may not have water in it, and your heating element may not be submerged in water, which means it'll get red hot and then prematurely burn out, or quickly burn out. So anyway, we're gonna let this system run for a while. We're at 163 degrees Fahrenheit, and we're gonna heat our mold up and then mold some parts. All right, well, I was successful in, well, mostly successful in molding a part, a few parts actually. What I didn't mention is that I actually had a stuck part in this mold as well, so I had to burn it out, and thus you can see some carbon on the side, which usually molding a few parts will clean up your mold pretty good. So yeah, but when I did mold my part, I see that there's a chunk of plastic that remains in the mold cavity. Fortunately, the new guide pins worked, so that all worked out. You can see that I almost stuck this part in as well. In fact, you can see how the ejector pushed out and it cracked the bottom of this part. So it was quite an ordeal, which wasn't on camera. Last time I basically burned out the part and then had to take the mold off and kind of disassemble half the mold. But there's still this chunk, and this is the molded impression of it that's deep inside of there. In fact, yeah, you can see it. See that white edge in the upper left? That chunk of plastic is still stuck in there. So I almost was in a situation where I'd have yet another part that was fully stuck, because I couldn't eject it with full eject force. But I heated up the core and I let everything sit for a while, and luckily this part did eject out. So what I need to do is get some hot copper pokers and basically push in some anchor holes and burn out that little chunk of plastic all the way in the bottom of this mold, and then continue molding. But I guess for the mission that is the topic of this episode, I was able to get our core pins either replaced or realigned. So this pin here is the one that I did some work on to straighten it because it was also bent. But again, we didn't cover that in this episode. And of course, just to add insult to injury, I had a stuck sprue there, so I'm going to have to burn that out with a hot poker as well. Anyway, my spidey sense says to stop and go ahead and release this video, and I will deal with this new challenge another day. All right, thanks for watching Dragonfly Engineering.